Welcome to the deep dive. We take your research stack, sift through it, and pull out what you really need to know. And today we're digging into two, frankly, massive headaches in modern software development. First off, how do you actually build applications around data that's naturally connected? Things like social networks, supply chains, maybe knowledge bases. It gets messy fast.
Right.
And second, how do you bring in the incredible power of large language models, LLMs, without getting completely tangled up in manual prompt engineering? It's tedious.
It really is, and developers have been juggling separate, often complex tools for these problems for far too long.
Exactly. But the research we've looked at points towards a potentially unified solution, something called the JAC programming language. So our mission today is to explore JAC. It's presented as a Python superset, which is interesting in itself. And it aims to solve both these big problems, the structure problem and the AI integration problem, using two core ideas: Object Spatial Programming, or OSP, and something called Meaning-Typed Programming, MTP.
Right. And what's really key here, I think, is that this isn't just Python with a few extra libraries bolted on. It feels like a more fundamental rethink of the programming model itself. We're shifting from this older idea where data and computation are kind of separate things.
Yeah, you fetch data, process it, send it back.
Exactly, to a model where the computation actually moves to where the data lives. And the promise for developers, it's pretty huge. They're saying you can model these complex, interconnected networks much more easily and then integrate powerful AI using basically a single keyword. It could drastically cut down the complexity compared to, current LLM frameworks.
Okay, so let's start with the basics then, the Python connection. If you're a developer already using Python, how easy is it to pick up JAC?
Well, that's definitely the entry point they're highlighting. It is a superset, so your core Python knowledge functions, control flow, variables, it mostly translates directly.
So the learning curve, at least initially, shouldn't be too steep?
Right. That familiarity is the hook. But JAC makes some immediate changes that push towards more robust code. For instance, type annotations.
Python hints versus JAC's rules.
Precisely. In Python, they're optional hints, useful but not enforced. JAC makes them mandatory. It requires type annotations, and that enforces type safety right from the start, which, when you're dealing with complex graph data, is actually pretty crucial.
Makes sense. Fewer runtime surprises.
Definitely. And another small but significant thing is the entry point for execution. Instead of that Python if name equals main thing, which, let's be honest, can sometimes feel a bit obscure.
Yeah, especially for newcomers.
JAC uses a very explicit with entry block. Execution always starts there. It just standardizes things, makes the code clearer, I think.
Okay, so the syntax feels familiar, but it's stricter, clearer in some ways. But you said it's a fundamental rethink. So where's the revolution? If it's not just syntax, what is it?
That's OSP. Object Spatial Programming. That's the core conceptual shift.
OSP. Okay, let's unpack this.
So, OSP is a paradigm designed from the ground up for graph-like data. Think about anything where the relationships between things are just as important as the things themselves.
Like that social network example we saw.
Exactly. In OST, those relationships, those connections, they aren't just pointers managed manually. They're first-class citizens in the language. And this allows computation to sort of naturally move or walk across this network structure.
Okay, contrast that with the old way, the social network example. Alice wants to be friends with Bob. In typical object-oriented code.
You'd probably have an add friend method on your person object, right?
So Alice.addFriendBob.
But friendship is mutual, so you also have to remember to call Bob.addFriend Alice.
Yeah. Two separate actions for one conceptual link. Easy to forget one, easy to introduce bugs.
Exactly. It's redundant logic, more maintenance. JAC aims to kill that specific problem by baking the graph structure into the language. It uses three main components.
Okay, what are they?
First, you have nodes. These are pretty standard. Think of your person node holding data like name, age, whatever, stateful entities.
Got it. Objects, basically.
Oh, kind of, yeah. But then you have edges, and this is crucial. Edges represent the typed relationships. So you'd explicitly define something like edge friends with.
An edge type.
Exactly. And then connecting Alice and Bob uses this special syntax, Alice plus friends with plus Bob. That single line creates the two-way link automatically.
Okay, that's cleaner. One line, bidirectional relationship.
And because the edge itself, friends with, is a first-class object, it can hold its own data, like maybe a since timestamp for when the friendship started or a closeness score. The relationship itself has properties.
Right, that's powerful. The connection isn't just a pointer, it's structured data.
Yeah.
Okay, nodes, edges. What's the third piece?
Walkers. This is where the computation comes in. Walkers are like little mobile units of code.
Oh, computation.
Yeah. You program a walker to start at a specific node, say Alice. Then you give it rules using a visit statement. For example, you tell it to visit all nodes connected by a friends with edge. As it travels, it can execute logic, maybe call a greet, function on each friend it finds.
So the code literally walks the graph you've defined.
Precisely. They're like little workers traversing the network, doing tasks based on the structure they encounter.
Okay, I see how that fundamentally changes things.
Yeah.
You're not just managing a collection of objects in memory anymore. You're actively modeling and working with a structured, traversable network. The relationships drive the logic.
That's the core idea of OSP.
So we've built this potentially complex, interconnected model using nodes, edges, and walkers. It sounds elegant for modeling, but what happens when you need to scale this up? Does this graph approach work for, say, millions of users?
Well, that's one of the major claims. It's designed for scale right out of the box. OSP naturally leads into this concept they call scale-agnostic programming.
Scale-agnostic, meaning?
Meaning, you write your core logic, your nodes, edges, walkers once. And that same code is supposed to work whether you're running it locally on your laptop for testing or deploying it to the cloud to handle a huge number of concurrent users.
Without changing the application code itself.
That's the promise. No major rewrites just to handle scale.
How does it achieve that? That sounds almost too good to be true.
It relies on a couple of key built-in features of the Jack runtime. The first one is automatic persistence.
Automatic persistence.
Yeah. Basically, any data that's connected directly or indirectly to a special node called the root node, Jack automatically saves it, persists it.
So no manual database setup, no ORMs, no SQL configuration.
That's the idea. You connect your important data structures to root, and the runtime handles saving and loading it. It aims to completely remove that whole layer of database management complexity.
Okay, that does sound like a developer dream, eliminating database chores.
Yeah.
But playing devil's advocate for a large-scale application, aren't you potentially sacrificing fine-grained control and optimization you might get with a hand-tuned SQL or NoSQL database?
That's a really fair point, and it's likely a trade-off, right? The goal here probably isn't to outperform a super specialized, manually optimized database in every single niche scenario. It's more about providing, say, 90% of the needed persistence functionality, but with like 0% of the usual setup and ongoing maintenance hassle for the developer.
Okay, so convenience and developer velocity over absolute peak performance in niche cases.
Potentially, yeah. And the second crucial feature for scale is multi-user isolation.
Handling multiple people using the app simultaneously.
Exactly. When you run your Jack application as a server using the jackserve command, the runtime automatically gives each connected user their own separate isolated graph. Each user effectively gets their own root node, managing their own data space.
So you don't have to manually write code for user sessions, data partitioning, making sure one user's data doesn't leak into another's?
Nope. The framework handles that isolation inherently because of the graph structure and the per-user root. It's a huge time saver, avoiding a common source of bugs and complexity in web apps.
Wow. Okay, so just by using Jack's core OSP structures and running jackserve, your application potentially gets persistence and multi-user scalability built in without extra infrastructure code.
That's the core value proposition for deployment, yes. Your app is designed to be cloud-ready and scalable from the get-go.
Right, that covers the structure and scale part. Let's pivot now to that other big promise, simplifying AI integration. Because, honestly, integrating LLMs right now often feels clunky. You spend ages on prompt engineering.
Oh, yeah. Iterating, tweaking, trying to get the exact wording right.
Then you get text back, and you have to parse it, try to wrestle it back into structured data your application can actually use.
Right. And then you need error handling, retries if the LLM flakes out or gives you garbage.
It's a whole complex layer just to ask the AI a question. This is where Jack brings in meaning-type programming, MTP, and this by-LLM thing.
Exactly. MTP is the concept, and by-LLM is the concrete implementation in Jack. And it's designed to basically obliterate that entire complex layer you just described.
Obliterate? How?
MTP works on a fascinating insight. Your existing source code, the names you give your functions, your variables, the type annotations you've already written, it's packed with semantic meaning. It describes intent.
Okay, good code is self-documenting, in a way.
Precisely.
Mm.
MTP leverages that inherent semantic richness to automatically generate the complex prompts needed to interact with the LLM.
Automatically, so the developer doesn't write the prompt.
Not in the traditional manual sense. Instead, they use the by operator. The example they give is defining a function like .strtr str by LLM at the end. Is by M. That keyword signals to the JAK compiler. Okay, look at this function signature. It's called translate. It takes a string called text. It returns a string. Use all that semantic context to figure out the best way to call an LLM to perform this translation task. It handles the API calls, the prompt construction, even validating that the output matches the expected return type.
Whoa. Okay, that little by LLM keyword is doing an enormous amount of heavy lifting behind the scenes.
A colossal amount, yes. It's abstracting away the entire prompt engineering and output parsing stack.
But is it actually effective? Does this automatic approach, relying on code semantics, produce results as good as or better than a carefully handcrafted prompt from an experienced engineer? Simplicity is great, but not if the results are poor.
That's the million-dollar question, isn't it? And the research suggests, surprisingly perhaps, yes. User studies showed MTP significantly cut down the complexity. They measured up to 10.7 times fewer lines of code needing modification to integrate LLM features compared to using other popular frameworks like LangChain or Llama Index. 10.7 times fewer code changes. That's a lot.
It's a huge reduction in effort. And interestingly, it wasn't just less code, it was often more efficient too. Because the system automatically generates and potentially optimizes the prompts based on the code structure, studies found MTP often resulted in lower token usage.
Fewer tokens means faster responses and lower API costs.
Exactly. They reported runtime speedups of up to 4.75 times and cost savings up to 4.5 times compared to the other methods in some tests.
That's really compelling. Can you give a concrete example? We saw that guessing game in the source material.
Right. That was a neat illustration. Instead of the game logic having hard-coded responses like too high or too low.
Which is fine, but a bit basic.
Yeah. The JAK version had a function, maybe give hint, guess.int, actual .int by Lyum.
Using by Lyum for the hint.
Right. So the game just calls give hint, and the MTP system uses the function name, the parameter names, guess, actual, and their types int, to ask the LLM to generate a helpful context-aware hint. Like, you're getting warmer, but maybe think about even numbers, or something more creative than just too low.
Exactly. The AI capability feels woven directly into the game's logic seamlessly, without pages of dedicated prompt handling code.
That makes the AI integration feel much more native, less like a bolt-on. But what if the code isn't perfectly named? What if variable names are a bit sloppy? Does the whole thing fall apart?
That's another interesting finding: robustness. The studies tested this. They intentionally degraded the quality of the naming conventions in the code.
Like using abbreviations or less descriptive names.
Yeah, simulating real-world code where maybe things aren't always perfectly clear. They found that MTP maintained high accuracy, even when up to 50% of the naming was suboptimal.
50%? Wow. So the system can still infer the programmer's intent, even from partial or slightly messy semantics.
It seems so. The underlying inference model is resilient enough to extract meaning, even if the code isn't perfectly pristine, which is good news for practical development.
Okay, this is starting to paint a pretty coherent picture. So what does this all mean for you, the developer listening? JAK seems to be offering this triple threat package. You get the Python familiarity, making it easier to get started. You get Object Spatial Programming for like naturally modeling and working with complex connected data. And then you get this revolutionary by operator, powered by MTP, that promises to dramatically slash the effort and complexity of integrating AI.
Yeah, I think that sums it up well. It's fundamentally about changing the developer experience, removing friction points. You get the automatic persistence, the built-in scalability with user isolation things you usually spend a lot of time setting up yourself. You get a programming model, OSP, that arguably maps much more directly to how real-world systems are structured, networks, relationships. And critically, you get a huge reduction in the cognitive load needed to bring AI into your application. You focus on what you want the AI to do, defined by your function signature, not how to trick a prompt into making it happen.
You spend time on the application logic, not the plumbing underneath or the intricacies of prompt syntax.
That seems to be the goal. Build the app, not wrestle the infrastructure or the AI interface.
Which brings us to a final, maybe provocative thought for you to consider. JAK's meaning-type programming hinges on the idea that an LLM can understand the intent behind your code just by reading it, your variable names, types, function signatures. If this MTP approach continues to work well, and maybe even gets better as LLMs themselves become more intelligent. What does that imply? Does it mean the future of integrating AI in software might depend less on becoming an expert prompt engineer crafting hyperspecific instructions, and more on simply going back to software engineering basics, writing clean, descriptive, well-named, well-typed code?
It's an intriguing possibility, isn't it, that perhaps the best way to prompt the AI of the future is just to write good, conventional, readable code. You're essentially writing the prompt already, just embedded in the semantics of your program.
Something to think about. You're already writing the prompt, you just don't know it yet. That's all the time we have for this deep dive. Thanks for joining us. We'll see you next time.